Each cubic centimetre of Earth's atmosphere contains hundreds of tiny solid or liquid particles, known as aerosols. Most of these particles are too small to be seen with an ordinary microscope, but without them there would be no clouds in the sky. Up to half these aerosols may originate from trace atmospheric vapours, which condense to form tiny molecular clusters. Once formed, the aerosols may eventually grow large enough to seed cloud droplets. However, this process is poorly measured and is limiting our understanding of clouds. Now it's being studied under controlled laboratory conditions by the cloud experiment at CERN. Atmospheric observations indicate that sulfuric acid vapour is required to form the embryonic aerosols, even though the atmosphere contains only extremely small amounts, less than 1 in a million molecules. At high altitudes, above 5,000 metres, where the temperature is below -25 degrees Celsius, these molecules collide together and stick to each other for a short time, but then generally separate. So something else must be helping them stick together. The cloud experiment has found that cosmic rays will do this. Cosmic rays are high-energy subatomic particles generated by supernovae in the Milky Way galaxy. They continuously rain down on our planet and collide with nuclei high in the atmosphere, producing showers of secondary subatomic particles. When this cosmic rain passes through the atmosphere, it knocks electrons out of some molecules which then attach to others. This results in positively or negatively charged molecules known as ions. When one of the negative ions collides with a molecule of sulfuric acid, the acid molecule becomes negatively charged. This enables it to attract other sulfuric acid molecules, causing them to collide at a higher rate. And when they do collide, the sulfuric acid molecules stick together for a longer time. With more sulfuric acid and water molecules arriving, a charged cluster forms and grows. Once it exceeds a critical mass, containing only a few molecules, the cluster becomes a stable aerosol. Rather than evaporating, it then continues to grow by further condensation of sulfuric acid and other vapours, in particular organic vapours produced, for example, by trees. The cloud experiment has found that charged clusters are up to 10 times more efficient than neutral clusters at forming stable aerosols. Many of these newly formed aerosols are lost by coagulating with pre-existing aerosols, but some may grow big enough to form new seeds for cloud droplets. These are known as cloud condensation nuclei, or CCN. The CCN are at least 50 nanometer in size. That is more than 50 millionths of a millimeter. When the relative humidity of the surrounding air reaches slightly above 100%, the CCN will seed droplets and a cloud will form. Depending on the temperature and the nature of the CCN, either a liquid droplet or an ice particle forms. At high altitudes, the ice particles form cirrus clouds. The cloud experiment has found that in the lowest 1 kilometre of the atmosphere, known as the boundary layer, this phenomena happens in a different way. In the warmer temperatures of the boundary layer, charged sulfuric acid clusters grow no larger than 3 molecules, while bigger ones simply evaporate back to 3 molecules. However, if a molecule of ammonia collides with a cluster shortly after a sulfuric acid molecule has arrived, it stabilizes the acid molecule and the cluster can continue to grow. Eventually, the cluster exceeds the critical size and becomes stable against evaporation. Then, once again, some of the newly formed aerosol may eventually grow large enough to form new cloud condensation nuclei, and so modify low-altitude clouds. The cloud experiment has found that atmospheric levels of ammonia are insufficient to account for the observed rates of aerosol formation at low altitudes. So other molecules must be involved. They are likely to be organic molecules, but their exact identity remains a mystery. Investigating organic molecules and also aerosol growth to CCN sizes are the next steps for the cloud experiment.